When writing equilibrium expressions, we only really report two things in the expression itself, because we're talking about the change in number of molecules per space. And so when we write an equilibrium expression, we can leave out any reactant or product molecule, which is a solid or a liquid. So we don't include solids and liquids in our equilibrium expression. So let's take a look at a couple of reactions and see if we can write the equilibrium expression for them. So here's Haber's reaction. Let's write it. So we would write that the equilibrium expression, Kp, because this is a gas phase reaction, is equal to the pressure of NH3. And since there's a 2 in the balanced equation, we raise it to the second power, all over the pressure of nitrogen, Pn2. In this case, it's raised to the first power, and then the pressure of hydrogen, raised to the third power. And so that would be the equilibrium expression for the first reaction. Let's try another one. And I will have to erase this. So give me a second while I do that. So while I'm erasing this, let's see if you guys can figure this one out. I'll give you just a minute. Okay, so for this reaction involving titanium and chlorine gas, what we'll do is we'll say the equilibrium constant. Since this involves multiple phases, we'll just call it K, equal to the products, TiCl4, which is a liquid, and so we don't include liquids in the expression, so we have nothing to put in our numerator, so we just put a 1. And then we do our reactants in the denominator. Well, we've got titanium, which is a solid. Again, we don't use that, but we do have 2 chlorines, so we say PCl2, and then since there's a 2 here, that means this is squared. So this would ultimately be a Kp equilibrium expression, equilibrium constant for pressure, because we have a gas here, and so Kp is equal to 1 over the pressure of Cl2 squared at equilibrium. Let's go ahead and try another one. And I'll erase this here. This time we'll do something involving hydrogen peroxide and it decomposing into water and oxygen. So again, it's products over reactants. So we have K equals our product. We have H2O liquid, so it doesn't get in there. But we do have O2 as a product as well. And since this is aqueous, we use a bracket. The oxygen has a coefficient of 1, so it's raised to the first power, all over our reactant, which is hydrogen peroxide, H2O2, quantity squared. So that would be our equilibrium expression for this reaction. And then finally what I'm going to do is I'm going to do the reaction one more time, but it's going to be written a little bit differently in that the reaction is now all in the gas phase. So the equilibrium expression will be Kp, since everything's a vapor, is equal to, now we're going to include H2O this time because it is a gas and not a liquid. So here H2O is included, whereas in the last one it wasn't. So we've got H2O squared, the pressure of O2, all over the pressure of H2O2 quantity squared. So that's how we write the equilibrium constant, or the equilibrium expression, I should say, for chemical reactions.